Hi guys, sound check. Okay, I think we should start. Well, okay. So let me recall you where we are now. So we were discussing a notion of a group and a subgroup. And now, at the end of the lecture, we discussed the cyclic subgroups. So now I want to describe all subgroups in the group Z of integer numbers with addition, and then I want to proceed with cosets and homomorphisms. So this will be the plan for today. So, okay. Where is the plan? Oh, okay, here it is. Okay, so let me recall this. So we have an abelian group Z of integer numbers with addition. And usually we just write Z without mentioning the operation because it's clear that the operation must be addition here. So we have a choice, like either addition or multiplication, but multiplication here doesn't give us the structure of a group. So we always use addition if the name of the group is Z. Now, I want to start with the claim. I want to describe all possible subgroups inside this group Z. So suppose that H is a subgroup. Then H is, well, then there exists a positive integer, actually non-negative integer, which is called natural, by the way. Yeah. There exists a natural number k such that H equals k times Z. The latter means that we consider all possible elements of the form k times m, where m is an arbitrary element in Z. So every subgroup of Z is of this form. Do you have any questions regarding the claim, the statement of the claim? So if you have any question, then ask or write your question in the chat. And now I want to prove this. So first of all, k times Z, this subset is always a subgroup. So this is a subgroup. Does anyone need me to prove this? So just in case, I want to recall you that we should check three properties, that the zero element is here. If some element is here, then its inverse, so the minus element is here. And if two elements are here, then their sum is also here. So these are the three properties we have to check in order to conclude that this is a subgroup. So this must be clear just from the definition. So now suppose that H is a subgroup. Now it must contain the zero element. So the neutral element must be inside H by the definition of a subgroup. Now we have two options. Either 0 is the only element, no. It's just the set of all natural numbers, 0 included, because 0 times z means that H consists of 0 element only. And this is also a subgroup. So this option is also allowed. Okay, so, and we will see this option here just right now. So we have two options. Either the 0 is the only element, so H consists of 0 only, or the second option, there exists an element in H which is not 0. So we have two options. So in this case, H is 0 times Z. In the second case, well, again, we have two options. Either M is negative or M is positive, because now it's not 0. But here, if M is negative, then since H is a subgroup, the inverse of M must be inside H, then minus M must be inside H, so, and minus M is positive. So in the second case, we may assume that H contains a positive integer. So in this case, we may assume that H intersect, well, let me denote it by n plus, by a non-empty set. So H contains a positive integer. Now, since it contains a positive integer, we may consider the least possible positive integer inside H. So let us denote K. So let's K be the least, so this is the smallest positive integer in H. And I want to prove, so our goal to show that in this case, H must be K times Z. So in order to prove this equality, so since H and K times Z are the subsets of Z, in order to show that two subsets are the same, we must show that the left-hand side, which is K times Z, is a subset of H. And the other way around, that H is a subset of K times Z. So first, we should show that K times Z is a subset of H. So why is this? Well, if K is inside H, then every power of K is also inside H, because H is closed under multiplication and taking inverse element, and the neutral element must be there. But in additive notation, power means K times M for any M in Z must be inside H, and this means that K times Z is inside H. So this inclusion is proved, has been proved. So now the second one. So now we want to show that actually H is inside K times Z. So why is that? So what do we need to prove here? We should take an arbitrary element M inside H, and we should show that M is equal to K times some M prime. So we need to find this M prime. So we should show that M is divisible by K. This is our goal. So now, well, if we take an arbitrary integer M, at least we can divide M by K with a remainder. So we can write M is equal to Q times K plus R, where R is between 0 and k minus 1. So it's strictly and k minus 1. So it's strictly smaller than k, and it's not it's it's equal or greater than 0. So this is just by definition of the division with the remainder. So now we can rewrite this as m minus q times k. So now, by our choice, m was an element of H. Also, k was an element of H. So then q times k is also an element of H. And then m minus q times k is an element of H, which means that R is an element of H. But this element is strictly smaller than k, and k was the smallest positive integer inside H. So there is only one option for R. R must be 0. So by the choice of k, so by definition of k, these three options, these three things implies that R must be 0, and we're done. So let me show you the whole proof. Do you have any questions regarding this proof? Should I repeat something? Was something unclear? Okay. Well, now I want to...
If we're interrupting, but for me, it is not totally clear. What does this multiplication means?
Which one? This one, k times z?
Yeah.
Okay. First of all, when you deal with integers, you have two usual operations, plus and multiplication. So I use the plus operation in order to get the group structure on Z, but I can use multiplication as well. Well, I mean, it doesn't mean that I do something with the group operation, but still I can use this operation to produce new integers. So just usual multiplication of integer numbers. But there is also the second explanation. We have this additive notation inside any group. So if I take an element M inside Z, or any group with where multiplication is denoted by plus, I want to consider like M plus M plus M plus M k times. So this is well, this is called a power of element. Why power? Because in multiplicative notation, when you use an element G in some group G and your operation is denoted by dot, like multiplication, and you consider the product of k elements, the same element G, then you denote it like G to the k, so like power. But in additive case, the same thing is denoted like k times M. So this is just a different notation for the power. So you just replace multiplication by addition, and then your power is replaced by this formal multiplication. But in case of integers, this formal multiplication by k, so it's just raising to a power, coincides with the usual multiplication of integers that you know. So is it clear?
Yes, now it's clear. Thank you.
Okay, no problem. But just in case, so this is just a different name for an operation, and when you use this additive notation, this is just raising to a power for the group operation. So it sounds silly when you use this terminology with addition. So at least we use a familiar notation, like when you like add M k times, you don't write m to the k. You just write k times m. So at least with notation, you're not confused. So these coincides with the usual operation on integer numbers. Is there any specific type of groups for which this theorem holds? Well, first of all, we started with a very specific group, which is Z. So this claim holds for the group of integers. Well, you can extend it to the group of reminders like Zn with addition. But I want to discuss this fact during this seminar. So this is not a general claim. It's a claim about the group Z. Did I answer the question, Andrei? Okay, so now, I mean, but okay, well, actually, well, to be honest, what you're saying, well, okay, so this claim means that every subgroup of a group Z is cyclic, because this is exactly the cyclic subgroup generated by an element K. And if every subgroup of a group is cyclic, then the group itself is cyclic, and the only cyclic groups are Z and Zn. But what this means, so somehow this is the most general case of this result. So you cannot extend it anymore. Well, first of all, the principal ideals, the principal ideal domains, well, they are somehow related to this result, but now I want to discuss groups, not modules over rings. So this is a more specific result. So the question is, in which direction do you want to extend this claim? I mean, it depends on your intent. Like, okay, let's don't waste time on this discussion, because somehow for the groups, this is the most general form of the result. And at the end of this lecture, I will explain why. Because I need the notion of isomorphism in order to explain the general form. Okay, so now I want to discuss cosets. Oops, wrong color. Cosets. So the modern algebra actually tends to study groups using subgroups and special types of subsets rather than elements. And the basic tool for this studying is cosets. So I want to give you a definition. So definition. First of all, we want to specify context. So we're given a group G and a subgroup H. So this is a group, and this is a subgroup. Now we need an element G from the whole group, the larger one. And I want to denote a subset of the form G times H capital, which is a subset of all elements G times H, where H is an element of H capital of our subgroup. So, and this thing, so this is a subset in G, and it's called a left coset of H in G with respect to G small. So this is left coset, the left coset of H in G with respect to G small. So left means where the small g is located. So if small g is on the left, then it's left coset. And in a similar way, we define a right coset as H times G small, which consists of all elements of the form H times G, where H goes through all the elements of the subgroup, and it's called the right coset. Let me put that here. The right coset of H in G with respect to G small. So the right here means that the element is on the right in this notation. This is how to remember the definition. Okay, let me give you an example of cosets. So I'll give you just one example, but in the lecture notes, I'll provide you with like 3 or 4 different examples. So, but I just don't want to waste time here during the lecture on showing all the possible examples. So let's the group G be Z with addition, and the subgroup will be 2Z. So if the operation is commutative, then the cosets, if the operation is commutative, if the group is abelian, there is no difference between left and right cosets. That's right, Anton. So, but in case G is not commutative, these two guys could be different. So it's possible that left and right cosets are different. But yeah, I'm going to give you an example with commutative operation. So here, if you take this group and this subgroup, then first of all, the subgroup itself is a coset. So here, since the operation is commutative, there is no difference between left and right cosets. So 2Z, which is formally 0 plus 2Z, is one example of cosets. And the second example is 1 plus 2Z is another example of cosets. And also you may find the same coset here, like 2K plus 2Z, and the same coset here, you can define it by 2K plus 1 plus 2Z. So this is the set of all even numbers, and this is the set of all odd numbers. So here you have only 2 cosets. If a coset is generated by an even element, then it gives you all even elements. And if a coset is generated by an odd element, then the whole coset consists of odd elements only. No, the cosets are not subgroups. For example, here, so this, okay, there is only, so the group itself form a coset, is a coset. So this is a subgroup, but all other cosets are not subgroups. So 1 times H is the only coset which is a subgroup. All the other cosets are not subgroups. And just Alexander, I prefer, well, I don't know, actually. I don't know how to expand this definition to something meaningful. Well, but in math, there are a lot of words containing this prefix core, so it's some kind of set, but, well, okay, so if you are given a set, then you may produce a subset, which is what is a set? A set is a bag of elements. So a subset is somehow a bag of elements which is smaller, which lies inside the first bag. But then coset means that you want to produce somehow dual operation. You don't want to find a smaller bag inside the first one, but you want to glue elements of the first bag and produce something called quotient set. So I don't want to discuss this. So there is some explanation, but I mean, I don't know how to expand this to something meaningful. But for me, this prefix just means something dual to being a subset. Well, in order to understand the rule for adding this prefix, you need to know the language of category theory. So all these notations and terms came from the category theory. Okay. So let me know the rule by the Russian. Oh, yeah, in Russian it's called смежные классы, yeah. So I didn't get your question. Okay. Now, so what do we want to know about cosets is that they form a partition of a group. So in general, if you have a group, so let me just present the results that I'm going to prove, because now I'm going to prove several statements, I'm sorry, before going further, I just want to, okay, I almost forgot to formulate one additional definition and prove one additional claim. So definition. So if G is a group and H is a subgroup, so this is a group and this is a subgroup. So if for every element G in G capital, the left coset of H coincides with the right coset of H, then the subgroup H is called normal. In this case, H is called normal. So in commutative case, every subgroup is normal, but in non-commutative case, there are not normal subgroups. And I just mentioned the example. We will discuss this example during the seminars, that if you take as a group S3, the group of all permutations on free elements, and if you take as a subgroup the cyclic subgroup generated by the transposition 1, 2, so this is the cycle between elements 1, 2, and the element 3 is fixed, then H is not normal. So its left and right cosets are different for some elements. And if you take as a subgroup here the cycle generated by the elements 1, 2, 3, then this subgroup is normal. So I just want to mention these two examples, and I don't want to check these claims right now. I just want to skip it. So normal subgroups is the special case of subgroups where there is no difference between all possible left and right cosets. Now, how do we check that a subgroup is normal? I just want to mention several simple tricks how to check this property. Claim. So again, we have a group and a subgroup, then the following are equivalent. The following are equivalent. First, GH equals HG for any element G in G capital. Second, GH G inverse equals H for any element G in G capital. And the third, GH G inverse is a subset of H for any G in G capital. All these three conditions are the same, and this simply means by the first condition that your group H is normal. So usually the third one is the easiest one to check. So if you want to check that H is normal, you just check the last condition here. So if you have any questions regarding these notations, so I will explain them during the proof of the claim. But just in case, Do you have any questions regarding the definition of the normality and the claim?
What is GHG to the power of -1?
Okay, so let me write it down here. So here, GHG inverse means the set of all elements of the form where H is inside H capital. Just by analogy. So if you want to multiply a set by some element, you just multiply each element of the set by this element. And since here we want to multiply on the left and on the right, you just multiply each element of your subgroup H on the left and on the right at the same time. This rule applies to any similar notation. Okay?
Okay, thanks.
So now,
Can I ask?
yep.
What is the symbol in the second? What is like this square subset equal or whatever this is?
Again, what does it mean?
Yeah.
Okay, so let me explain this here. So H is a subset in G. When you multiply it on the left and on the right, you will get some different, probably different subset in G.
Yeah.
So you have two subsets, and the equality, well, the equality is the usual equality of subsets. So, I mean, these and these are the same subsets inside G. This is what the equality means.
Oh, that's equality.
Yeah, oh, it's, okay, I see. There is problem with this sign. I'm sorry. This is the usual equality. Yeah, that's because my handwriting is awful. Okay, I hope now it's clear. So here, so also, probably it would be better to write a picture. So you have a group G, and here you have some subgroup H, and when you, so in general, you when you multiply it by an element G on the left, you will get something like this, some different subset. And when you multiply it by an element G inverse on the right, let me write it a different way. So you may get something like GHG inverse, and you want them to be the same. So the picture shows the case when H and GHG inverse is not the same. So, but if this happens, then H is not normal subgroup. But if this guy is always the same as this one, then H is normal.
And
okay.
So
yeah.
H is a normal subgroup if any of these holds.
Yeah. So by definition, we require the first claim to hold. But since all these three are equivalent, it doesn't matter which one we check. Okay.
I'm sorry, I didn't understand. It have to be all properties holds or only one or two?
Only one of them, because
only
the
one
following are equivalent. Yeah. The first claim implies the second,
okay.
the second implies the third, and the third implies the first one.
Okay.
So there is no differences between these three claims.
Mm-hmm.
Okay, no problem. So now let me show you how this is done. So if we have this, so then multiply this equality by G inverse on the right. You'll get this equality. And if you want to go back, you multiply the second equality by G on the right, and you will get the first one. So this is how you prove. So the multiplication by this element implies that from this equality you get this equality, and multiplication on the right by the element G implies that from this equality you get this equality. Is it clear? And do you have any questions regarding this proof? So I have what was shown here that 1 is equivalent to 2. So 1 and 2. Okay, it's clear. So now, well, I think it should be clear that 2 implies 3. So let me recall you that 2 means that you have equality for all possible G, and 3 means that you have inclusion for all possible G. But equality, well, it's just a partial case of inclusion. If you have equality, you have inclusion. So now, the only thing that we need to prove is that the third item implies the second one. So if you have inclusion, we actually have equality. So it's impossible to have a proper inclusion here. So that's okay. And we need to show that 3 implies 2. So now we have GH, G inverse inside H for all G in G. Okay? And we want to prove the other inclusion.
But we can multiply one from the right part on G, and
yes.
On the right, multiply on G from the right part, and we somehow have to multiply by G minus 1 on the left part, and then we will have backward inclusion, like
No,
the same.
Not yet. Not yet, but okay, that's almost the proof. Yeah, you're right. So let's multiply these on the left by G inverse and on the right by G. So I want to multiply it on G inverse on the left and by G on the right. I'll do it in one step. So then you will get that H is a subset of G inverse H, G, for any element G in G capital. Well, this is not exactly the opposite inclusion, because here you have G, and here you have G inverse, and here you have G inverse, and here you have G. But the crucial point is this. This holds for any G. So you may apply it for G inverse instead of G. Since it holds for any G, so it also holds for G inverse. So in particular, it means that H is a subset of G inverse to the power of minus 1 H G inverse, which is GH G inverse. And this is the inclusion we need. So, and also this holds for any G inside G. Is it clear?
Yep.
Okay, if you have any questions, just ask them right now, and I'll try to proceed. Okay, so now what I want to show you is this. Let me announce, so I want to clarify what kind of results I'm going to prove, because I'm going to prove several formal claims. So I want you to know what is the goal of our actions. So suppose I have a group G and a subgroup H. So I want to draw a picture. So this is a group G, and this is a subgroup H. I want to show you that the left cosets form a partition on a group G, which means that if you consider some family of left cosets, then the whole group G is a disjoint union of some left cosets. So the cosets are like here. So you just cut your group in pieces, and each piece is just a left coset of your group. So this is the first claim I want to prove. And the second claim, well, if all these, well, if H is a finite subgroup, then all these cosets have the same amount of elements as the group H itself. So all left cosets have the same amount of elements as the group H. So the cosets give you a partition of group G into pieces of the same size. And this leads you to some combinatorial strategies, some combinatorial tools when you want to study groups. So this is roughly what I'm going to prove. And the same claim holds for the right cosets. But if you consider right cosets in general, so H as the right coset, well, it will be exactly the same subset, but other right cosets will probably be different, like HG1, HG2, etc. So you will get another partition with right cosets, but it still will be partition, and all the right cosets will have the same amount of elements as the group H. And if the subgroup H capital is normal, then of course these two partitions will be the same. So this is our goal. And this is called the Lagrange theorem. Okay, so let me start. Claim number one. So if you have a group and a subgroup, so this is a group and this is a subgroup. So, and we have two elements, G1 and G2 in the group G capital. Then you have two options. The option number one, left coset G1H coincides with the left coset G2H. Or the second option, so either. Or the second option, G1H intersects G2H by an empty set. So what I'm showing here is that if you have two left cosets, then either, what about zero? What do you mean, what about zero? A coset is not a subgroup. It doesn't contain zero. Only one coset, which is H, contains zero. Well, if zero is the name of the neutral element. So what I'm saying here, so it is exactly what is shown on this picture. So every two cosets, they, well, if you have two cosets, they are either the same. So for example, G1H may coincide with some G prime H. Or if they are not the same, they do not intersect each other. So only two options. So it's impossible to have something like that. G1H, G2H. So this is impossible. You never have that. Okay. If you have any questions regarding the claim, please ask. But if not, then I'll proceed to the proof. Okay. So now, suppose we have these two cosets. Well, if they do not intersect each other, then it's okay. We are done. There is nothing to prove. So we may assume that they actually intersects. And suppose that G is a common element which belongs to the intersection. So since G belongs to G1H, this means that G equals G1 H1 for some element H1 in H capital. Since G belongs to G2H, well, by definition, it's of this form for some element Michael, I see what you wrote, but I don't understand what you mean. Okay, so I'll skip. If it's a question, then please could you reformulate it or just ask orally, because I just don't understand what you mean here.
Okay, I'll ask later, because я не успеваю за вами записывать, я просто пока это писал, вот я не успеваю, я потом спрошу после.
Okay, no problem. Okay, no problem, no problem. So, by the way, the lecture notes will be uploaded today. Okay, now, so we have, so let me repeat what has happened here. So we consider, we assume that these two subsets intersect. So, and G is a common element. So now we want to prove that in this case, they are actually the same. So now, by definition, since this element is here, we have this equality. Since this element is here with this, we have this equality, because this is just by definition of the left cosets. And now, so now we have that G1 H1 equals G2 H2. So if we multiply this equality by H1 inverse on the right, we will get G1 equals G2 H2 H1 inverse. And I want to denote this element by H. So we have simply G1 equals G2 times H. And since H capital is a subgroup, this element H is also inside H capital. So now, using this equality, let me show you that the two cosets are the same. So I want to show you that G1 H capital is a subset of G2 H capital. So for that, I want to show that every element of this guy is an element of this guy. But let's take an arbitrary element of this guy, which is of the form G1 H prime. This is just an arbitrary element. Now, since we have this equality, G1 equals G2 times H small, this is the same as G2 times H prime. And this is an element of H capital because H was a subgroup, it's closed under multiplication. But now we can see that the left-hand side is represented in the form G2 times something from a subgroup. But by definition, this element is inside this coset. So just by definition, the right-hand side is in G times H capital. So we have the inclusion. And if we want to prove the other inclusion, we will use that G2 equals G1 H inverse, which we get by multiplying this equality by H inverse on the right. And the proof is exactly the same. And that's it. So let me show you the whole proof and the claim. So the claim was that the two left cosets, any two left cosets, are either the same or they do not intersect each other. So if you have any questions, then please ask. If not, then I want to prove a second claim, which, so
I have a question, and this is still same question which I tried to write. For example, if our group is like integer numbers and multiplication,
but it's not a group.
It's not a group.
Yeah, integer numbers with multiplication is not a group because, for example, 2 is not invertible. 0 is not invertible. With respect
well, now I got the problem. Okay.
So yeah, so when we mention integers, we always use addition because that's more or less the only operation giving us a group structure on the Z. Well, we can produce other operations. They will be non-natural, but this is the only natural operation that gives you a structure of a group on Z. So multiplication is never used because of that. So what I've shown here is this, that every group is divided into a disjoint union of cosets. So every element of a group, because of this claim, belongs to exactly one coset. So, and now I want to make a remark. So it may happen that you have two different elements in a group, but their cosets are the same. It may happen. For example, if you take an arbitrary element in the subgroup H and an element 1, which is also inside the subgroup H, then H small times H capital is the same as H capital. Because if you multiply all elements of a group by an element, by one fixed element, you will get all possible elements, because multiplication is invertible. So this is multiplication by an element of a group is a bijection, so you will get all possible elements. So, but this equality also means that this is the same as 1 times H. So it may happen that two different elements give you the same cosets. So an interesting question is how to check that two different elements generate exactly the same cosets. And yeah, by the way, there is a second example. If you take H to be the whole group G, then there is only one coset, which is the whole group G. So any two elements gives you exactly the same coset. So this is just a trivial example. This is an example number 2. So let me explain how to check this condition. So what should you verify looking at the elements G1 and G2? So the claim is G1H equals G2H if and only if G1 equals G2H for some, I mean, there exists H in H capital that G1 equals G2 times H. So if and only if. Well, indeed, well, if you have this equality, G1 belongs to the left-hand side because G1 times 1 belongs to the left-hand side. So G1 is always here because it equals G1 times 1. Why if H? Oh, why this? Okay, let me go one step back. So there was a question why we have this equality if H equals G. Well, okay, let me erase all of this and just, I will repeat it later. So this simply means that G1G equals G2G. Okay, so why is that? Well, it is enough to show that G1G equals G. But if you, but okay, G1G is obviously a subset of G. But you also have that G1 inverse G is a subset of G. And multiplying this by G on the left, G1 on the left, you will get that G is a subset of G1 G capital. So that's why you have these two inclusions. This simply means that when you multiply all possible elements of a group by one fixed element, you will get all possible elements of a group. So you just somehow permute the elements of the group G by multiplying by one specific element. So that's why if your subgroup is the whole group, then every coset is exactly the whole group. Andrei, is it clear? Okay, it's good. So so it might happen that two different elements give you different cosets. So now, okay, let me formulate a claim, but I'll skip the proof. For example, as an exercise, or we will discuss it during the seminar session, because I need a bit more time to complete the lecture. So suppose that we have, so I'm saying that two cosets are the same if and only if there exists an element H from H capital such that G1 equals G2 times H small. So this is the condition you have to check for the elements G1 and G2 if you want to check this equality. So this is the only case when two different elements gives you exactly the same cosets. And if you multiply this equality by G2 inverse on the left, you will get a similar condition, an equivalent condition. So that's another form of this equality. So G2 inverse G1 belongs to H. So these three conditions are exactly the same. So this is the form, the easiest form to verify that two elements give you exactly the same cosets. So that's how people usually check. They either check this or this. But let's skip. The next thing I want to explain is this, that all cosets have the same amount of elements as the group H. Let me formulate claim. Suppose G is a group and H is a subgroup. This is a group and this is a subgroup. And let's, for simplicity, assume that H is finite. So it has only finitely many elements. So this notation means the amount of elements inside the set H. Well, it's true in case of an infinite subgroup, but it's hard to explain what it means that two infinite subsets have the same amount of elements. So I just don't want to torture you with all this generosity. I mean, we don't need it. We will use all the results in case the group G is finite. Yeah, that if you know what this means, but it's exactly mean that two sets are equivalent. Oh, that's good. But okay, for simplicity, I will assume that H has finitely many elements, but the proof will be general. So if you understand what it means, then you will get it. So then, for any element G, the amount of elements in the left coset of with respect to G is the same as the amount of elements in the subgroup H. Now, so this is the claim. So for every finite subgroup, the amount of elements in every left coset is the same as the amount of elements in the group itself. So now, how to prove this? Well, let's consider a map multiplication by G on the left, which takes any element X to the element G times X. So this is a map, multiplication by a fixed element G. Well, this map is a bijection. Why? Because there is an inverse map, which takes any Y to G inverse Y times Y, which is multiplication by G inverse on the left. So these two maps are inverse to each other. So that's why this multiplication is a bijection. So being a bijection is the same thing as having an inverse map. Okay, but now, if I take a subset H, then by the first map, multiplication by G on the left, we send this subset goes to this subset. Here, I need two dots. So this is also, so since this was a bijection and this subset goes to this subset, then this is also a bijection. But since this is a bijection, then the amount of elements here is the same as the amount of elements here. So is a bijection. So now you see this if H is infinite, then this means that these two sets are equivalent, as you mentioned. So, but if they are finite, this simply means that the amount of elements in H is exactly the same as the amount of elements in G times H. And we're done. So this is the proof of the claim. So let me show you again the claim itself and the proof. So the proof is really simple. It follows from the fact that multiplication by any element in a group is an invertible operation. So it's a bijection, because we can describe its inverse explicitly, like here. So if you have any questions, please ask. If not, then I want to proceed to the proof of the Lagrange theorem. Okay, so let me formulate a claim. So claim, suppose G is a group, H is a subgroup, and G is finite. Then, the first claim, the amount of left cosets, the number of left cosets is equal to the amount of elements of group G over the amount of elements of group H. So the part of the claim that this number is divisible by this number, so the result is integer, and the result is equal to the number of left cosets. And the same claim is true for the right cosets. So if you want to count the number of the right cosets, you count the number of elements in the group G, the number of elements in the group H, you divide this by this, and this is the number of left or right cosets. So in particular, we see that even if the group is not normal, so the left and right cosets are different, the number of left and right cosets is exactly the same. And this is the number, and it equals this number. Okay, so let me show you the proof. Probably you already see how to prove this. So I will prove the result for the left coset. For the right coset is exactly the same. So now, from the previous claim, which is the claim about the partition, the group G is a disjoint union of some cosets. So the picture is this. So if you have a finite group, then it's represented as a union of k different cosets. That was the claim, like, if you don't remember, this is this claim. Since all the cosets are either the same or they do not intersect each other, this simply means that the whole group is this disjoint union of the left cosets. The second thing from the previous claim, we know that all these cosets have exactly the same amount of elements as the group H itself. So now, if we want to count the amount of elements in the group G, we just count the amount of elements here, plus the amount of elements here, etc., plus the amount of elements here. So this is the amount of elements here, plus etc., plus the amount of elements here. But since all these guys have the same amount of elements, this will be this times the amount of elements in H. But from the choice of K, the K is exactly the number of distinct left cosets of group H inside G, because we know that every other coset is, well, I mean, it's either do not intersect any of these, but this is impossible because they cover the whole G, or it coincides with at least with one of them. So there are no other left cosets. So this is the whole list of the cosets we have. So K here is exactly the number of left cosets. And this completes the proof. So here is the claim and the proof. If you have any questions, please ask. But I have another question. Should I go a bit faster, or the speed is okay?
And could you tell me, please, where did we prove that that the left coset of H cardinality is equal to cardinality of H?
Oh, it's this claim.
Okay.
Okay. No problem. It's okay. That's good. I mean, since it's, well, I mean, algebra is very formal, so it's probably good to have a slow pace. But if I'm too slow or I'm too quick, just tell me. It's okay. I will try to adjust my speed. Okay, it's totally fine. That's good. Okay. So now, since we have this claim, we can give a definition. So if G is a group and H is a subgroup, so it's a group and it's a subgroup, then okay, the index of a sub, and we assume that G is finite. So in case of a finite group, then the index, this is called index, index of H, is the amount, is the number of left cosets, or the same is the amount of the right cosets. So the number of cosets, it doesn't matter left cosets or right cosets, is called the index of the subgroup. And the Lagrange theorem is this. Lagrange theorem says that if you have a group and its subgroup, and the group G is finite, then the amount of elements in G is equal to the index of H times the amount of elements in H. And we actually already, we have actually already proved this claim here, because this is exactly this claim where we just used the new notation for the left-hand side in each equality. So, and this is called the Lagrange theorem. Now I want to discuss several corollaries of the Lagrange theorem. But again, if you have any questions, please ask. If not, then I'll proceed to the corollaries of the Lagrange theorem. So corollaries. The corollary number one. So if we have a subgroup, then its order, the amount of elements of a subgroup, divides the amount of elements in the group. The second one, if we have an element of the group G. So here I'll always assume that G, the conditions of the Lagrange theorem. So G is a group, H is a subgroup, and G is finite. So G will be always a finite group. So now if we have an element G of G capital, then the order of the element divides the order of the group. Well, this is because the order of the element is equal to the order of the cyclic subgroup, and by the first corollary, the order of the cyclic subgroup divides the order of the group. Well, the next thing is this. If we have an element of a group, then if we raise it to a power being the order of a group, we will get the neutral element. Well, this follows from the fact that the order of the element is equal to the order of element times some k. That's the previous claim, that the order of the element divides the order of the group. And now if we rise an element to this power, it simply means we first rise it to this power and then to this power, and rising to each element to its order gives you 1. So g to the power g capital is the same thing as g to the power order of g and then to the power k, but by definition of the order of the element, this equals 1, so 1 to the k, and the result is 1. So this is the third corollary. Now, oops, I'm sorry. The fourth corollary is this. So suppose that G has prime number of elements, or P is prime. Then for any element of G distinct from the neutral element, G is equal to the cyclic subgroup of G small. So if you have a group of prime order, so if you have only a prime number of elements, then your group must be cyclic, and it's generated by every non-identity element. So if you take any non-neutral element, then it will be a generator of your group G.
And
So
why G
why?
small is not, it does not belong to G capital?
What again?
Why G small does not belong to G capital?
Oh, it was a mistake. That's I'm sorry, that just a misprint. It's the opposite. It belongs to the G capital. I bear in mind two conditions. G must be an element of G capital, and G is not equal to 1. So I just smashed the notation into one piece. So thank you. Yeah, that was a mistake.
Can you please show the corollary two notations before?
What again?
Can you please show two corollaries before? Yep, this one. Thanks.
Yep.
Okay, thanks.
No problem. No problem. So now, well, I'm a bit quick now since I have 5 minutes, and oh no, I have 25 minutes. Am I right?
No, you're not right. The lecture ends in 5 minutes.
Oh, in 5 minutes. Okay. So it's okay. So yeah, I want to formulate and prove all the corollaries. So so now, why this is true? So if the group consists of prime number of elements, so okay, let's take first of all, if group consists of prime number of elements, then it has at least 2 elements, because the least possible prime number is 2. So there is always a non-neutral element. So I can always find an element G which is not 1. Now, I just consider the cyclic subgroup generated by this element G small. This will be a subgroup of the group G. And we know that this subgroup is not equal to the subgroup containing just one neutral element, because G itself is not neutral, so there is at most 2 elements inside this subgroup. So the number of elements here is not 1. But now we know that the order of subgroup divides the order of G, which is prime number. But there are only 2 options. This number is either 1 or P. It cannot be 1 because this subgroup contains more than 1 element. So the second option holds. So since P is prime, we have the number of elements here is P. So this subgroup contains exactly the same amount of elements as this group. So these are the same. So since G also has P elements, then G capital is this, and we're done. And now I have 2 minutes for the last corollary. It's called the little Fermat theorem. So the corollary number 5. So it says that, so the little Fermat theorem so let P be a prime number. And A is an integer which is not divisible by P. Then P divides A to the power P minus 1 minus 1. Or you may reformulate this in the following manner. So A to the power P minus 1 equals 1 modular P. So this is the little Fermat theorem. So why is this? Well, let us consider the group ZP star with multiplication. ZP star means that we take all numbers from ZP which are co-prime with P. Here, since P is prime, this simply means we take all non-zero reminders with respect to P. So the numbers from 1 to P minus 1. So this is a group. And the order of this group is P minus 1, because ZP contains P elements, and we excluded the 0 element. So now we have P minus 1 element. And now if we take an arbitrary number in Z, which is not divisible by P, it simply means that if we take A is equal to R modular P, where R is a number between 0 and P. So now, okay, so since A is not divisible by the prime number, R is not 0, and now A to the power of P minus 1 is the same as R to the power P minus 1 modular P. But this is the claim. But here, what's written here, we raise an element R of this group to this power, which coincides to the order of the group. So because of this corollary, let me show you which one. Because of this corollary, which is the corollary number 3, the later is equal to 1 modular P. And that's it. I hope that was clear. I mean, it seems to me like it wasn't totally clear, but okay. The time is out. So if you have any questions regarding the proof or any material that has been presented, please ask. And okay. Well, okay, the lecture notes will be uploaded today. I will upload the whiteboard as well. Thank you for attendance, and I'll see the first group in a couple of minutes on the seminar. Thank you, guys.